If, yeah, do we all see the slides? Well, I can start giving the introduction. And yes, as already said, very welcome to this afternoon session on the very new developments working and perhaps not working within AI for the ocean and sea ice applications in the Arctic Ocean or in the Arctic. I thought of well, I'm Anna Nikolopoulos from I've just been moving from the Norwegian Polar Institute to the university in Tromsø. I'm co-chairing the Arctic ROOS now with Vidar Lien at the Institution of Marine Research here in Norway. And we thought that we should just show some slides on where we are in the landscape, which is pretty complex. Just for those who are not very familiar with it. We are part of EuroGOOS. We are the Arctic tentacle of EuroGOOS, which in turn is part of a vast system of the Global Ocean Observing System, the GOOS, founded under or by then the IOC back in the 1990s, and since then working for the well-being of the oceans as part of a global effort. And in this vast system, we are 1 out of 5 regional systems, regional operational oceanographic or observing systems. There are many acronyms here, as you can see here at the very top of our image, together with our sister organizations in the Baltic Sea, Northern West European Shelf, and the Mediterranean Sea, and also outside, in the seas of Ireland, Biscay, Iberia region, try to cooperate here all together for the missions of EuroGOOS. And yes, we work as the European voice, right, to both stimulate, advocate, strengthen, promote, and mobilize all the oceanographic activities with focus on operational systems and those entities, but really including almost everything by now. And we do so through taking part, for example, in the EuroGOOS task teams. I hope you know about these. Otherwise, I refer also to the website to get to know specific groups that can be living for shorter or longer periods of time and bringing specific questions within specific contexts forward. You see some examples of those, also the working groups that we are trying to send representatives for the Arctic then to the European aspects. And you can make the list long for the current priorities, but examples of what we work with, aside this major task to respond to calls and be involved in programs and projects, and also, give a response to in different matters. The last few things on the list have been to, initiate or and make make a startup of the Arctic ROOS Sea Ice Task Team, which I think calls themselves SIT, led by Jari Hapala nowadays, for moving forward with harmonizing in situ sea ice observation practices. We need everyone to mute the microphones. Yeah. In close dialogue with the Copernicus Marine Sciences in situ groups as well. And also a major thing on the list, particularly now for 2025, is to take active part in the development of the suggested Arctic Ocean observing regional alliance, which is overarching. We in Europe have the Arctic organ as us, Arctic ROOS, but several nations we don't really have a pan-Arctic entity yet. And we are in the works to propose the structure and function for such one to GOOS and also the SEON groups through another task team. Also, the last few years, we have collaborated closely with the Ocean Prediction DCC Arctic Regional Team, which we co-host this very webinar through, and Heather is coming up in just a second. And we are very happy about that. It's been thriving, and also we try to have annual webinars and connect our communities and work through that. And well, of course, needless to say, trying to also have connect closely to our members every year through general assemblies. So yes, that is the intro. I shouldn't take more time than this, but please visit the EuroGOOS website, which we are underneath, and maybe you can just scrutinize those pages and get to know more. And I think I hand over to Heather now, our happy co-host.
Thanks, Anna.
And I stop sharing.
And I will try to start sharing. Okay. Thinking. Okay, I hope you can see my screen. Right. Yeah, so as Anna said, we are collaborating closely between the Arctic ROOS and the Ocean Prediction Decade Collaborative Centre. So I will very briefly explain what this is. As part of the UN Ocean Decades, there is an ocean prediction section, and I am leading the Arctic regional team as part of this. So ocean prediction is explained as a 10-year voyage over the decade, run by IOC, UNESCO, and it's taking us from the ocean forecasts that we have at the beginning of the decade to lead to the ocean forecast that we want, ultimately. Can I just quickly ask, okay. Is there a bar of stuff across it's just on my screen. Okay, great, thank you. So during this decade, we are aiming to work together, create a stronger community within ocean forecasting across the globe to ultimately provide better forecasts and more users and more ability and capability to forecast in the regions, particularly that don't have so much capacity at the moment. And there are two pillars to this. So the first is creating this community, and this has been established much in the line of as Anna was showing before, the GOOS Regional Alliance is a sort of been the basis for establishing these different regions. So there are 9 different regions that the globe has been partitioned into, and each of these are gathering their own communities to work together. The Arctic one has been slowly building up for a while, and across the globe we've had some difficulties with some of the teams being completed with their steering committees. Now that is all in place. And so we're hoping that this year we are able to start moving forward with Arctic Regional Team activities, ultimately combining scientists, users, private sector, and others involved with ocean forecasting to, the thing this year will be identify gaps in these systems and ways forward. And I'll explain later how we can get involved with that. Just quickly, the other pillar is a more technical pillar. So it is built around an ocean forecasting co-design team, where there are about 30 experts, each with forecasting related expertise in the globe. And they are working together to establish an architecture, so the standards, tools, and best practices associated with forecasting systems to try to create a more unified setup. And just quickly, I thought I'd throw this in there. Why are we interested in an AI workshop? Well, in the Arctic, there are a number of issues, as we know, with ability to model and therefore predict the system. And this is a schematic of how a forecasting system could work, where you have inputs, various different sources, models and a simulation working together, and then some outputs and downstream users. And these little robots are appearing where some of these processes are being supplemented or assisted by AI for various reasons. And this is what we want to try to understand today, as to help with our understanding of the Arctic forecasting landscape, and therefore what Ocean Prediction DCC can do to help that. So a very brief summary. This is what we're trying to achieve: an active community of users, scientists, and policymakers, to also support the technical work. And we're really hoping to develop this year, working with the Arctic regional team now. If you want to be involved with the Arctic regional team and you're involved with forecasting in some capacity, please email me at the address at the bottom. And I've also put a website in orange here. One of the main things, and one of the achievements of last year, was to establish this atlas of forecasting systems and people involved with forecasting around the globe, of which you can see an image there of the ones available at the moment. If you're involved, please add yourself to this atlas, and you can then receive newsletters and be contacted more easily about the developments and how you can participate going forwards. So I will leave it there, and we can now start talking about AI. I guess I can introduce the first speaker, since I was the last one talking there. So we have an exciting program today, and the first one is Julien Braja from NERSC, who will be giving an overview, I believe. I will let him introduce what he'll be talking about now.
Yes, thank you, Heather. So good afternoon, everyone. So thank you for inviting me to this workshop. As you said, the program looks really appealing. You're right. And I will give like a short overview of what and how AI can be used for accelerating and enhancing the forecast in the Arctic. So it will be like, of course, I had to select some aspects, so it's not comprehensive at all. But the hope is that it will introduce some of the presentation that will be done later in the afternoon. So let's start with what we are dealing with. So here you have an example of ocean sea ice forecast. So you have two variables here, which is the sea ice concentration and the sea surface temperature. So this is one forecast produced by a system developed here at NERSC, which is called Topaz, and that is distributed on the Copernicus Marine Data Store. And yeah, just to show you that this is operational, it works, and it gives some useful and accurate forecast. But now, if we want to talk about AI, the first question we want to ask is what AI should address in those ocean and sea ice forecasts. And I will start with some limitations of the current forecasting system. So the first limitation is, of course, as you know, the computational cost. Second one being some bias in the model and in the forecast. And the third one is the limited spatial resolution of those forecasts. So I will illustrate each of the aspects. So for the computational cost, I showed you the Topaz forecast. Just to produce one of these forecasts, you have to use a lot of CPU hours. So for one forecast, it's 1,200 CPU hours for one forecast cycle. You can leverage a parallelization, but still it's very costly. Now, if we talk about bias, you can see here for the same system, the bias on the ice edge length compare with ice charts in Nordic Sea and Barents Sea. So it's not exactly Arctic, but just to give you an example, that to show that you have some bias of thousands of kilometers in the ice edge, and this is for all system. It's not particular to this example. So huge bias in those forecasting model. And if we talk about resolution, we have, for example, for the topaz, a spatial resolution of 6.5 kilometers, while there is a requirement or a need to have resolution up to a couple of hundreds meters of resolution, which is far to be reached. So these are the current limitation of the systems. And AI can. I'll try to change the slide. Sorry. Yeah, AI on machine learning. I prefer to call that machine learning, but AI may be more sexy. I don't know. Is an approach that could address that. So I will show you now very briefly and very generally how we could include AI and machine learning in a CI forecasting system and why it helps, basically. And to do that, I will introduce the difference between a physical-based model, which are the models that are used now to do the forecasting, and the data-driven model. So the physical-based model, you start from physical principles, physical equations, so thermodynamics, dynamics, that you will discretize. You will use numerical scheme to integrate numerically those equations. And at the end, you have basically a computer code that takes that will take an input state of the CIs, for example, and will give you the next state of this of the system. So this is a classical physics-based forecasting system. Now there is another way to deal with this problem, which is a data-driven model. So instead of starting from physical equations, you will start from data. You will train typically a neural network to train on those data. And at the end, you have something that looks very similar. It's still a computer code that predict the next state of a system given the initial state. Of course, there is like a trick because the data, they are not coming from nothing. And most of the time, they come from assimilation in a physics-based model. So the physics-based model has not disappeared here. It's just a bit hidden in the dataset. There is a special case of that. If you don't use observation, if you just use a physical-based model, so you have data that are just model simulation, then we call the data-driven model, we call that emulator. It's just like a wording precision, but I will use sometimes the term data-driven and sometimes the term emulator when the system has only been trained on a physical-based model. And actually, that worked quite well. So I will give you a couple of examples of data-driven model in the CIs. It's not, again, comprehensive. It's just a selection. And I will not give too much detail on some of them because they will be presented later on in the afternoon. So the first one is IceNet that will be presented by Andrew, I think, today, which is an emulator for, or data-driven model, sorry, for CIS concentration, which is mostly targeted toward a seasonal forecast. But there is also a version for a shorter term. But I don't give too much detail because Andrew will talk about this, I guess. The second one is the one by Charlotte Durand, which emulates the CI thickness that has been trained on NextTeam simulation. NextTeam is a CIS model, which is a pan-Arctic, and yeah, emulate the CIS thickness for only a fraction of the cost of a physical-based model. So all those emulators that I show here, they are running at a very small fraction of the cost compared with a physical-based model. And another one for very short-term prediction at high resolution is developed at Met Norway, and it has been trained on CI chart. Oh no, sorry, on OCSAF. Okay, so there are examples of data-driven model. But still, so data-driven models I have explained. So you can, sorry, I'm coming back just quickly here. So for example, if you look at this example of IceNet, you see that those data-driven models, they achieve some of the objectives that has been that I have developed before. So they are reduce the cost they're reduced, sorry, they're running, as I mentioned, as a reduced cost. So they are all very quick to run. And also they reduce some bias. If you look at the IceNet, the accuracy is higher than the physical-based forecast. And this is the case also for the other examples. So we have achieved some of the problems that were in a physical-based forecast, but we still have some issues. And I can mention some of them here. The first issue is that depending on the way it's trained, but generally those emulator or data-driven models, they are not very realistic. They smooth the output. And here I give you an example of a very simple emulator of a quasi-geostrophic model. Here you have the physical model on the left, and in the middle, we initialize both models with the same initial state, but you have the neural net emulator, and you see that obviously, even though the general dynamics is well reconstructed, there is a smoothing of the different structures that you can see in this system. So this is of course a very simple example, but this is something you can see in a lot of different type of emulator. Another problem with those emulators is that if you run them for a long time, they can diverge, or they can they can blow up. And here, this is quite an old example, but again, generally, it's hard to find a figure of a model that blows up. And I really appreciate the fact that those authors have presented a figure of a model that blows up, because it's something that happens a lot in all those emulators. And here you have you have in time, so the x-axis is the axis, on the horizontal axis is the time, and the vertical axis is the state, which is a one-dimensional state model. And you see that the physical model is running for a very long time. And if you look at the emulator, it seems to do a very good job at the beginning. It's again initialized with the same state, and the first time step seems to work very, very well. Again, at a fraction of the cost, so it's always what we want to achieve. But then after a while, it will blow up. And this is also something you encounter with a lot of emulators. And the third problem that I have not illustrated here is that those emulators, they're good for the data they have been trained on. So basically, if you have trained your emulator on past historical data, it's hard to say how it will generalize under other forcing. And this is particularly the case if you want to apply that for future climate. So this is another problem with those emulators. And the solution to that, so sorry, I don't know how much time I have left. Okay, still 5 minutes, I would say. So the one way to address that is to go toward a hybrid model. So this is a other aspect I'd like to introduce today. So this hybrid model. So here again, you have the physical-based model, very, very costly, and that give you the prediction from the initial state. You have the full data-driven model that does the same thing, but only at a fraction of the cost. And you can also say, okay, in this physical-based model, I have some components that are not so expensive to run. For example, some low-resolution core. And there are some components of, for example, some parameterization that are very expensive to run. So the idea of the hybrid model is to keep the cheap components as physical-based model, and to emulate or represent the expensive component as a data-driven model. And then you will build a hybrid model where that contains both the physical-based component and a data-driven component. And I will give two examples of those hybrid approaches and how they can also address the three problems of the physical-based forecast, which are, again, the bias, the cost, and the resolution. So the first example is to use a hybrid model for bias correction. So this is a very easy, very straightforward way to see the program. You have a physical model that does a prediction, and on top of those physical model, you will add a neural network model that will correct the error of the physical model. So here you don't address the problem of the cost, because you don't modify the physical model, but you address the problem of the bias. And here is an example of a paper published last year from Cyril Palerme et al., where you see as a function of the lead time, the error in terms of ice edge distance, so the distance between the forecast and the true ice edge, for different system. So you have the Topaz, the previous version of Topaz in red. You have also a version of Topaz that has been corrected for bias in yellow-brown color. You have the persistence starting with ice chart in green and the persistence starting from OCSAF AMSA2 in black. And you can see that deep learning solution, which is in blue. So this hybrid model, which has run the Topaz forecast, but corrected the Topaz forecast using a neural network, is outperformed from day 2, outperform any other forecast. So this is my first example, using hybrid for bias correction. And another example is to use hybrid for the problem of resolution. I told you that resolution was an issue with physical forecast. And this is, of course, linked to the problem of cost. It's costly to run forecast at high resolution. So what you can do is you can build a hybrid model where you run your physical model at a low resolution model, and you add the neural networks to do only downscaling. So here, this is what I have done for CI thickness. So I start for a CI thickness field. So here, this is CI thickness that mimic the CS2 smooth product. And I will produce an ensemble of high resolution. So here, on top of doing a hybrid model, I'm doing a probabilistic or generative hybrid model, because from one input, I have an ensemble of output. So actually, in all those outputs, I don't know how good you can see all those figures in your screen, but on one of these input is actually the ground truth. The other are generations. So you can see that they are all very similar, but we can play the game to try to guess which one is a good one, and the good one is this one on the second column, top row. So you see that we can generate this way a very, very realistic output for a very for the cost of a low resolution model. And you can run this, so you can run the model, you can run your downscaling on super resolution model on top of the resolution model and create like kind of hybrid model. So here, this is the low resolution model CI thickness. Here you have the high resolution physical model, but very costly to run. And here you have the CI, the AI or machine learning generative CI thickness model, so hybrid model. So you see that we can recover some of the small scale of the physical model. So I think this is it. I would just summarize my what I said so far. So I tried to convey the idea that we can use data-driven models based on AI or machine learning to speed up the physical model, to correct the bias of the physical model, and to enhance the spatial resolution of those models. So this is, in my opinion, the main application of AI for a forecasting model. There are other applications for observation that they will be introduced by other people later on, but I don't touch that now. Those data-driven models can have challenges with stability, realism by blurring the output, and generalization. And all those challenges can be addressed by using hybrid model and or generative models to overcome these challenges. So this is what I have. So yeah, I guess it's good to keep some time for questions. Oh yeah, and sorry, one last thing. The presentation is shared, so there I've put some reference at the end. And if you're interested in those topics, of course, you can contact me by email. So I let that here to leave my email if you're interested to contact me about that. So now I'm open to questions.
Thank you, Julien. So this is Vidalian, and I will be the chair of the first part of this webinar, the first session. Thank you for this very nice overview, Julien. So we have time for one quick question. if you have longer questions or discussion points, there will be a discussion section or session at the end of the webinar. So you can also keep your questions for then if it's long. But if there are any very quick questions, please. Okay, if not, we go on with the first part of the webinar. So in the first part, there will be 4 presentations, and then they will span different uses and use cases, going from in situ data and satellite data, and also modeling and assimilation and forecasting. So the first one out is Tore Wulff from DMI in Denmark, and he will talk about deep learning-based retrieval of Arctic sea ice information from SAR and passive microwave. So please, Tore, the floor is yours.
Thank you. I'll try to share my slides. I hope you see my slides now.
Yes, perfect.
Thank you. All right. So good afternoon, everybody. First of all, thank you so much for having me. My name is Tore Wulff. I'm from the Danish Meteorological Institute, and I'm going to present some of the work we do at DMI on the retrieval of Arctic sea ice information, primarily from satellite-based synthetic aperture radar using deep learning techniques. And of course, I would like to acknowledge the efforts of the entire team here at DMI working on this topic. So I'll start off with a bit of motivation as to why the SAR is an interesting sensor for monitoring sea ice, and how sea ice products derived from SAR can complement existing sea ice products that are primarily derived from passive microwave radiometers. So here on the left side of the slide, I have an example of the OSI 408 sea ice concentration product from OSISAF, which is based on the AMSR2 sensor. Now, passive microwave radiometers such as AMSR2 have been used to monitor the Arctic sea ice for many decades. And these instruments, they provide data sets that are crucial for studying and understanding the long-term sea ice trends in the Arctic region, but the spatial resolution of the observations, and then by extension, the derived sea ice products, is quite coarse, oftentimes in the order of tens of kilometers. On the other hand, SAR sensors have quite high spatial resolution. So Sentinel-1, for example, has a spatial resolution of around 100 meters when operated in the extra wide swath mode. So there is a potential here for SAR-based sea ice products to offer a bit more detailed insights into the Arctic sea ice. The complication with SAR observations, however, is that these observations can be ambiguous and very difficult to interpret. And therefore, we need quite advanced computer vision techniques in order to automate the interpretation of these observations. And for that reason, we turn to supervised deep learning, and specifically convolutional neural networks to carry out this task of retrieving the sea ice information from SAR images. And as many of you will know, supervised deep learning algorithms, they require a lot of training data with accompanying ground truth information in order to train models with good predictive performances. And ground truth information is not really that easy to come by in the Arctic region. And the end goal here, of course, is to train a robust model that is able to generalize to the entire Arctic region for all seasons. And in order to do that, we need a vast and diverse training data set that covers as many different sea ice conditions as possible. And one source of label data that we can use for training is regional ice charts. So these ice charts are drawn manually at the national ice centers around the world for maritime users, for the safety of navigation in ice-infested waters. And these ice charts, they are abundant and they cover vast geographical areas, and they are available throughout the year. So they match our requirements for a label data set fairly well. But of course, there are also disadvantages to using ice charts as the label data when we train our model. One thing is human subjectivity, as the ice charts are drawn by manual interpretation of satellite observations. And also the ice charts are provided in a vector format consisting of relatively large polygons. I have an example here at the bottom of the slide. So here we see the sea ice concentration from an ice chart and the corresponding SAR image. And as you can see, the fine detail in the SAR image is not really captured in the ice chart. So this means that when we train a model using ice charts as the label data, we are not able to fully exploit the high spatial resolution of the SAR sensor. So in summary, ice charts are not the ideal label data, but nevertheless, in our opinion, it's the best label data that we have available at the moment. And then a very brief overview of the model itself, which we have named the DMI-ASIP model. It is a convolutional neural network that follows a modified UNet architecture. It fuses Sentinel-1 SAR images with brightness temperature observations from AMSR2 to produce these CIS maps. And it is a multitasking model with 3 separate decoders, so simultaneously predicting 3 different CIS parameters. So while our presentation here today is focused on the CIS concentration, the DMI-ASIP model is also predicting the CIS stage of development and the CIS flow size. So together with our partners in the ESA-sponsored AI for Arctic project, we have compiled this matchup dataset consisting of Sentinel-1 images, brightness temperature observations from AMSR2, and ice charts very kindly provided by the Greenland and Canadian Ice Services. And this dataset consists of more than 5,000 of these matchups from 2018 up to and including 2021, covering the Greenland waters and parts of the Canadian Arctic. So this next slide has a little bit of math. It's about the CIS concentration retrieval and uncertainty estimation that we developed for the DMI-ASIP model. So the CIS concentration parameter in the ice chart labels in our training dataset is given as discrete CIS concentration increments from 0 to 100% in steps of 10%, which gives us a total of 11 CIS concentration classes. And then for each grid point in a given input, the DMI-ASIP model is trained to output a vector with non-normalized scores for each of these increment classes. And these vectors are then normalized using a softmax function. And what we then end up with for each grid point is a vector that represents a discrete probability distribution over this set of 11 CIS concentration classes. Unfortunately, we know empirically that modern neural networks, they tend to be poorly calibrated, which means that we cannot immediately assume that the softmaxed output from a trained model represents a true probability distribution. This is something that we need to assess, and there might be a need for post hoc calibration. And one way to assess the calibration of a trained model is to plot the accuracy as a function of this softmaxed probability output from the model, which is what we've done here on the right side of the slide. So here, any deviation off of the diagonal represents miscalibration. And we find that our model is slightly miscalibrated, so we use a post hoc calibration technique called vector scaling to improve the calibration of the model. And then finally, given a well-calibrated model output, the CIS concentration and the associated uncertainty can be computed as a weighted average and a weighted standard deviation of the 11 CIS concentration classes with weights given by their respective class probabilities, which is what is provided by the model. And this approach solves 2 issues for us. So firstly, this results in a continuous CIS concentration output, even though the model itself is trained on these discrete labels from the ice charts. And secondly, it provides an estimated uncertainty characterized by standard deviation, which of course is very important if products based on this methodology is to be used in safety critical applications, for example, in the context of operational ice charting or also for data assimilation. So now we return to the example from the first slide, but this time with the output from the trained DMI-ASIP model as well. So in the top row, we have the SAR image and the OC408 CIS concentration product. And in the bottom row, we have the uncertainty as well as the CIS concentration output from our model. And here we see that the DMI-ASIP model achieves a higher spatial resolution. We see a higher level of detail, especially along the CIS edge, which is also where the ice charts are typically quite detailed. Then since November of last year, I hope this animation is playing for you, we have been providing Arctic-wide CIS products based on the DMI-ASIP model as part of the Copernicus Marine Service. And these products are daily level 3 mosaics on a 500-meter grid based on Sentinel-1, containing information about the CIS concentration, the CIS stage of development, and the flow size. And we provide these products in near real time, but also as a 10-year reprocessed data set of the entire Sensor-1 archive from 2014 to 2024. And what you see here on the left side of the slide is an animation of rolling 7-day mosaics of the sea ice concentration in these level 3 products. And then before my time is up, I would like to mention a couple of internal DMI use cases for the sea ice information that we can derive using the DMI ASIP model. So first up, the Greenland Ice Service is located here at DMI, and they provide sea ice information for the local communities and mariners in the Greenland waters. And they are in the process of evaluating DMI ASIP to assess how the ice analysts at the Ice Service best can benefit from these AI-based sea ice products. And what we provide to the Ice Service is a continuously updated mosaic of DMI ASIP sea ice concentrations in a vector format that is compatible with the GIS software that the ice analysts use in their daily work. This is we have an example here on the right side of the slide of such a mosaic product. And as a reference, on the left side of the slide, we see a composite of manually produced regional ice charts from the Greenland Ice Service from around the same time. We also have a sea ice modeling group at DMI running the coupled ocean sea ice model called HiCom Size. And they made the switch not too long ago from assimilating a daily level 3 sea ice concentration product from OSISAF to assimilating level 2 sea ice concentration products from both DMI ASIP and OSISAF, which I think is a cool new development. And using this new assimilation scheme, they've been able to improve the accuracy of the model. So I have an example here on the slide from the 1st of February this year. So in the top row, we see how this new assimilation scheme helps in the removal of false ice off of the west coast of Greenland. And in the bottom row, we see the SAR observation from Sentinel-1 and the corresponding sea ice concentration output from the DMI ASIP model. And that's actually my last slide. If you're interested in the operational products that we produce for Copernicus, I have a QR code here on the left side. And on the right side, I have a QR code for a paper that we published on the DMI ASIP model, which also goes a bit more into detail about the validation of the model. So thank you for listening, and I'm open to any questions.
Thank you, Tore, for that very nice overview and the interesting talk and use cases. So while the next presenter is preparing, we have time for a question or two from the audience. And if not, it's possible to use the chat or save your question for the discussion session afterwards. Yeah, I don't see any hands. So if there are no questions, I think we just proceed with the next presenter, which is Penelope Wagner from the Met Office in Norway, and we will talk about short-term sea ice forecast evaluation for maritime uses in the European Arctic. So please, Penelope, the floor is yours.
Thank you very much, and thank you very much for the invite. And let me just share my screen for a moment. Can you all see this?
Yes, looks good.
Perfect, thank you. Okay, so yes, I'm Penelope Wagner. I am the head of the Sea Ice Operational Service at Met Norway. We're based here in Tromsø, and I'm just going to give you a very brief overview of what we're doing to evaluate some of these forecasts. So first, I just want to provide a summary of what we do. We're actually mandated to provide sea ice information for the area, for Met Area 19, the area between Greenland and Russia. So you can see we actually cover a large area, and we provide the sea ice concentration charts from Monday through Friday. And this is our main mandate is aligned with the International Maritime Organization to support navigational safety and allow mariners to make good decisions on the route planning. And our ice analysts, they provide the ice information similar to how the weather forecasters provide the weather information on a routine basis. So what we're doing, we're actually looking at the sea ice on a tactical basis, but what we actually really need is to provide more information to our users and our ice analysts on short-term sea ice forecasts, meaning up to 3 to 4 days. This is really important for us, and especially in our area, we have predominantly first-year ice, so it is very susceptible to shifting wind patterns and weather conditions. Wind is one of the biggest drivers for our area, and then we also, not only do we have a lot of new and first-year ice, we have a mixture of older and new ice together, so this causes a lot of potential hazards for navigation, and it really challenges us on how we're able to monitor this in near real time. So right now we do provide sea ice concentration, but what we really want to do is expand our sea ice portfolio to include sea ice forecast, stage of development, so sea ice type, the sea ice edge, and also include this with the cryohazards. And we want to include a layer of, to provide a limit of icebergs. We don't normally have a lot of icebergs in our area around Svalbard and Barents, but we're actually starting to see a lot more. And we share the East Greenland side with the Greenland Ice Service. So this is good that we're actually trying to work together on addressing some of these issues of iceberg tracking and archiving. So I wanted to just kind of explain our situation of how we actually use these products, or how we can use these products. We're really investigating this right now. So ideally, what we're trying to figure out is how do we determine the best probability and impacts with the current suite of data sets we have. And this is for all ice services. All ice services, they do produce ice charts, but they're in the process right now to evaluate automated products. It's not very easy, of course, because of some of the challenges and limitations of the sensors that we see during the melt and summer season. So I really appreciate a lot of these efforts that are going into improving the automation with this. But this also impacts how we're able to use the sea ice forecasts. So we really want to try to find the balance between being able to represent where the actual sea ice is, and also include important parameters such as the ice edge. And this is something that we're looking at from the lens of our users. But I do want to say, though, we're actually also the users of products. It's not just the maritime community. Our analysts are the users of these. So right now we're really trying to put together a more controlled evaluation setup so that we can do both in parallel. So right, some snapshots and outlooks. Let me know if I'm getting a sign that I might have unstable internet connection. So let me know if I pause. So case studies are very good to show what some of these capabilities are for models or automated products. But what we want to see is how they perform on a regional and seasonal area over time. And we want to look at them over a certain period so we can really get an idea of how they're performing. So what we're trying to do is we're going to expand our product portfolio to try to include more weekend charts, ice type or stage of development, pressure ridges and leads, and then also include these iceberg layers and sea ice models. And then we also want to try to provide more information if we have to respond to an incident. So this is not trivial. And so right now we're putting together these evaluation of I'm just going to go through the evaluation of how we're looking at some of the ice, the parameters from these forecast models, such as ice edge and the ice drift. So right now what we're looking at, we kind of did a really coarse mapping of how we view the situation of the products that are on the shelf and what we need to do to integrate them in our system. So as an ice service and as an operational ice service, there's no products that are off the shelf that we can just take and put it in. We actually have to break these products down and build them back up into our systems, whether it's something that's actually integrates more geospatial information, but also you can see in the color scheme here, the yellow boxes are products that exist, but they need more work. The green boxes are products that do exist, but they need to be integrated in our systems. But what we're really looking at are the red boxes, that these are new and that must be developed. So from our situation, from the ice service, we're really focusing on the red boxes. So we actually need to develop these products within our services. They're available within, say, Copernicus or other data centers, but we will actually need to figure out how we can use them on a routine basis and make the most out of them. So a lot of this is really looking at the evaluation part, you can see. So what we're looking at is we broke up to focus on how these forecasts look at the ice edge. We broke them up into 3 different regions in the Barents Sea, Svalbard, and Greenland. So this is easier for us and to look at the ice edge, because then we can actually look at this more in detail and figure out where we can, where the model performs better and where it doesn't. And then if it doesn't, if there's a lot of uncertainty in some areas, then we can go through some more auxiliary data to figure out why this is. And we're also, you can see, we're looking at the sea ice drift, and I'll just provide an overview of that. So looking at the sea ice edge, we're looking at the ice edge integrated error, and this is something that's been around for a while. So this is how we're applying this and visually representing this. So you can see how these different models. We're looking at the Barents EPS that's developed within Met Norway. The GOOS is now the new ESPCS. This is something that's like relatively new, so we're looking at that right now. We're looking at the NEXUM, and then also the AICE model that's also developed within Met Norway. So you can see there's kind of a spread. On the black areas is the integrated ice edge error, and you can see that the blue area is the ice chart. And so we're also looking at the persistence. So you can see on, for example, on Svalbard day 2, the predictions. If we have a close-up of this, it doesn't look very significant when you're looking at the broad big picture part of it, but when you actually zoom into it, you can see the spread is within tens of kilometers on just this snapshot. This is January, so this is actually a pretty good agreement. When we go into the melt and summer season, we'll probably expect it to be, or we have seen that the spread is a lot larger. So you can see how we're looking at this. We're comparing the model evaluation forecast. We're looking at seeing how this performs over multiple days. So the displacement of how these models perform over a few days. And you can see actually we're looking at the regional variation of each of these. So from this, we can actually get a snapshot of how the forecast models perform on the ice edge for each region. You can see Svalbard, they actually have a really good agreement, but we also have the coastline that constrains the ice edges here. We have a much larger spread in the Barents Sea. This is probably because there's a lot more new ice and it fluctuates very quickly in this area. So again, this is something that is still under evaluation. And so you can see that we're looking at the median ice edge error distances. So the first day, the persistence normally beats them, but as we go to the second day, we see that the models start performing a little bit better. So this is something that we can maybe look into to think that this could be something that has to do with the initialization. And then we're also looking at the temporal variation to look at the spread of how this performs throughout the year. Now the top area is the temporal variation for each region. This is over the last month, but you can see the second figure is just focusing on the ice edge distance for the Barents Sea. And what we're seeing is, as an example, if we look closely at this, you can see actually in the summer that has a lot more agreement than in the other areas. And this was kind of not really expected, but then I think this could be a suggestion that the forecast, the spread is so large because it's when we're outside of the summer areas, we're seeing a lot more new ice being developed and it's drifting around. So I think this is where we're seeing the large spread between the different forecast models. And then we're also looking at the drift evaluation. You can see that we're connecting these with the IABP drift tracks. We're only using the 4 models for this, and we're looking at this on a routine basis. Now we have a monthly report that we're putting out that includes all this information so we can keep track of it. But this year we're able to, we're going to try to integrate more of the analysts into this. So you could see we also represented the distance and direction error in the same ways we did with the ice edge. We're looking at the error bars, we're looking at the spread of the different forecasts. And for all of us, I think this is a better way to really assess this. This is something we're actually trying, and we're gonna look work with the Greenland Ice Service also as we're trying to evaluate some of these different products to make sure that we're all on the same page when it comes to how our analysts view these differences. So this year is going to be a really exciting year. We're going to try to get some of these products in our in a training production line and task some of our analysts to do a more routine analysis of this. And then through this, we're going to try to develop a more operations to research, research to operations feedback loop. But with this, it's going to, we're going to have to look into how much time it's going to take. Well, first of all, how the performance of the forecast models are throughout the year. We're going to look at how we can use them. And then we're also going to see how much time it's going to take to maybe provide input into this. And then so that we can make sure that we can also put out the routine products at the same time. So this will, so for us, we're actually going to have to put a lot of effort into developing a more comprehensive training program for our analysts and build upon that. So overall, what we're really trying to get at is that the information we provide is in the highlighted areas, which is relevant, representative, and reliable and actual, and of course, overall accessible. So this is all I have today. And like I said, this was a really short overview. So I didn't go so much into what we're actually seeing with these, but we expect to be able to have more statistics and information later on in the year.
Thank you, Penelope, for this nice overview. We have time for a couple of questions or comments. Yes, I think there's a question from Julien.
Yes, hi Penelope. Thank you for the nice talk. It's just a question about do you see that the arrival of AI-based products will change something in the evaluation, or do you see that it will be evaluated exactly the same way?
No, I think that I mean, actually, the evaluation, the evolution of the AI is showing a lot of promise. I think that it's going to really help us to be able to understand what areas we can automate on a routine basis, and what areas we're actually going to have to put more effort into in adjusting throughout the year. So I think that once we get a better handle on that, I can see that this will really impact some of the improvements in how we assimilate some of this data into the sea ice forecasts.
Thank you.
Any other questions before we move on to the next speaker? If not, we move on from sea ice and into the realm of biology. The next speaker is Tsuyoshi Wakamatsu from the Nansen Center in Norway, and he will talk about machine learned-derived synthetic BGC profiles in the Nordic seas and its operational applications. So please, Tsuyoshi, the floor is yours.
Okay, I want to share my screen. Let's see. There you go. Do you see?
Yes, very good.
Okay. Hello, everyone. Thanks for giving this opportunity to present this work. And so today, as Lian said, that I'm going to give a talk about biochemistry in the Arctic Ocean. And then this the application of the AI or machine learning started 7 years ago. And then the motivation was for the operational purpose, but it's expanded the meaning, and then I'm gonna summarize what I am doing, and then what is the future the perspective is. So this is the surface chlorophyll map taken by the satellite ocean color sensor in Norwegian Sea in the springtime. I think it's a June time. So there is a very strong the spring bloom on the surface, especially in the Lofoten Basin. And then, but satellite ocean color data, of course, can see only surface. And then we have the question that what's happening under the, at least below the top, the 10-meter depth, where beyond the satellite, the radio signal can penetrate. So this is the diagram of the typical seasonal cycle of the chlorophyll seasonal cycle. This is created by the composite of the chlorophyll measured by the biogeochemical algal floats in Norwegian Sea. And so starting from the early spring in a deep mixed layer depths associated with the very light bloom. And then when the mixed layer depths become the shallower, and immediately it will trigger the strong bloom. And then that lasts through the summer, and then it gradually decayed towards the winter condition. And the many process happening, and especially this is very important because this phytoplankton biomass is the foundation of the marine food web. And then also this is the trigger of the biological carbon pump. And as you can see that BGC algal floats can beautifully measure this profile very well, but issue is that compared to the so-called core algal, which measuring the temperature salinity profile over the last 20 years, this is BGC algal profiles, the density in the space is quite sparse yet. On the right panel, this is a sample case at the snapshot. The yellow dots are location of the BGC algal floats, and then red floats, the dots are location of the core algal. So compared to the core algal floats, we do not measure the BGC the profiles the much smart the density is very, very sparse. So the question is, so as I said, I had a idea that assimilating this BGC algal profile to our operational system, but seeing this the scarcity, we start to ask question that is there a way to increase this density artificially using the AI power? So that's the motivation originally. So this is a system. Quickly, I will explain. We are using machine learning system called the hidden Markov model. This is a relatively the classic system compared to the modern the deep layer system, but it works quite beautifully well. And then the diagram shows that the one x is the something you cannot observe time series, and the y is something you can observe. And then having those information, we construct the probability matrix that help you to infer, given the observation, for example, you observe the y, and what is the most likely condition of x is. And then this works not only at the single time, but also this red the curve means that there is a backward propagation for information. So it will make sense through the specific period of time. So this is a smoothing problem in the mathematical term. So this system works quite well with the ROOS system, because the ROOS system is measuring the water column information over the time, relatively in the constant the period. And then there is a good match of the surface information with the satellite ocean color data. And so you can produce this matching along the algo data. then aim is to having this system, can we estimate back the condition X only using Y information? So here's the things. So we will give the surface dimension, not only the chlorophyll, but because knowing that the dynamics of spring bloom is controlled by the atmospheric condition and also mixed layer depth condition and also light condition, we will give the different kinds of the surface parameters we can obtain operationally. So this is a sample case. For example, we have a short wave radiation and the C-surface temperature and the C-surface chlorophyll too. So as a surface information. And we have a set of those information on along the core algo float. And we have a chlorophyll profile, and then we train the hidden miracle model. So next stage is to, given this set in a different location along the algo floats, core algo floats, where we don't have a chlorophyll observation, can we estimate the chlorophyll profile good or not? So this is a sample case. So this is the green spaghetti diagram is the old the algo float, business algo floats available in the last 10 years in Norwegian seas. And then the red spaghetti profile is one of the longest lived business algo, which measured the good 6 years seasonal cycles. Top is the original data, and then bottom is a cleaned one. So in order to give this information to the machine learning system, we need to clean up the data. And then, so it's a gap-free data. Then what we perform next is the matching the algo float location with the surface information. So this case on the right, on the top two panels show the satellite SST and satellite chlorophyll data. So along the profile locations, you see the 6 seasonal cycles. And then below, the left is the observed profile. So we test this system along the BDC algo, where we know the solution. And the right is estimated profile. So as you can see that the internal cycles difference between over the years quite captured well on estimated profile. And also the depth of the mixed layer depths that give the information that how deep the chlorophyll, the bloom reached to the subsurface. So so we have a quite good sample case here. And then so this package is available on the GitHub right now, and you can test how things works using the numerical model output, the chlorophyll profile data. And then, for example, this is a sample case on the numerically the produced chlorophyll seasonal cycle with many the high frequency the limit cycle. So as you see that it's not only estimating the surface data, but also subsurface where the satellite observation cannot see, and even there is no the bloom, you can the system can predict the subsurface bloom quite well. So this is ongoing activities based on this system. So we are now trying to extend this system not only to chlorophyll profile, but to estimate other carbon-related the parameters. One is particulate organic carbon, and under the ESA project funding, and then other is the DIC, is the dissolved inorganic carbon. And so this carbon, the information will help us to close the carbon cycles. And then we have the science case study, the project using the SWOT, the ocean, the sea level anomaly data with the high resolution. And then the last one, this comes just started this year. So we finally try to operationalize. Sorry. So we are trying to operationalize the system through with the help of the EuroGOOS, the community. So now we are going to produce this data as operational product in 3 years. And then also we perform the intercomparison with the other systems, which is working for the similar purpose. And in the future, I like to do that using more the clean the surface data, for example, the gap field satellite data, which is ongoing under the ESA scope project. And then adding the sea level anomaly as observable data to get the information from the eddy impact to the ocean biogeochemistry. And then retraining of the zone profiles. Zone profiles is the set of the X profiles based on the larger data set, and then is going to happen in the next 3 years. And then eventually we like to replace this HMM with the deeper layer inference AI, for example, with the CNN. And then after creating those data set, now we can reach to our original goal to assimilate this artificially inferred BZC profile to our operational system. Thank you. So this is my talk today.
Thank you, Tsuyoshi, for a very interesting talk. Any questions? I don't see any hands. Or does Heather? Please go ahead.
Hey, thanks, Yoshi. How many Argo profiles are would be optimum to be able to use this as
Yes,
the largest extent and time possible?
Larger the better, of course. And then so we maximize the available data by collecting the many floats in the Norwegian Sea in this the pilot studies. So data only available from 2013, and then after cleaning up the data to fill the gap, and we need to discard some short-lived profile data, and we have only about 20 to 30 profiles available. And then that's enough to produce what I saw. But I believe that longer the observation period becomes, and then more seasonal cycles data becomes available, and that will increase our accuracy, I believe.
Thank you.
Yeah, and I think a small follow-up from my side would be the applicability into other regions. I guess you can't just extrapolate from what you do in the Norwegian Sea into the Arctic, for instance, or shelf areas like the Barents. So, what do you think about that? I guess
Yes.
you will need specific data from specific regions, right?
Yes, that's a very good the question, and because this is it's a data driven the product. So without data, you cannot easily extend it to the other region where data is not available. But however, for example, there is an empirical relationship to infer from surface to subsurface in the Arctic, the ocean too, and which was studied based on in situ data. And then what they did was to making the section an ocean, assuming that the same rule applied to this section. So the smaller number of the sample data can apply to the region. So under such the assumption, so we need a kind of regionalization. And then I believe that we can extend the area it can cover.
Okay. Yep. Interesting. So thank you again, Tsuyoshi.
Thank you very much.
We move on to the last speaker of this first part. And we continue to stay in the ocean in situ, but now on physical parameters. So the next speaker is Aska Yamakawa from IMR in Norway, and she will talk about the use of AI in quality control of CTD profile data. So please, Aska, the floor is yours.
Yes, thank you. I'm going to share it now.
Yes, it's perfect.
Okay, yes. Good afternoon, everyone. And thank you for inviting me today. My name is Asuka Yamakawa. Our AI proposal was granted by Mercator, and we started a new project in September last year. So we do not have a much result, but I want to share what we have done the last 6 months and what we want to do in the future. This is our...
Sorry, your presentation disappeared.
Oh,
Yeah,
now
we see
yeah.
it. Yes.
So this is our CTD data pipeline. Once data center receives CTD data via satellite, data is stored in the database, and we set the automatic QC and generate netCDF and publish as a near real-time product to Copernicus. And this data is used for forecasting, and forecasting product is published again in the Copernicus Marine Service. Also, the human expert review the data or quality of the data, and we publish a delay mode product with a manual QC flag. And this data is updated once a month. And I forgot to say, near real-time product is updated every hour. Then we had a question. If we improve the quality of automatic QC, can we increase the quality of forecast product as well? And second question is there any way to reduce the human workload? Because manual QC takes a lot of time. So we wanted to reduce this human workload. Then we thought machine learning may help to solve these questions. I'm not sure. Am I sharing my screen now?
No, it disappeared again. Every time you switch slides, it appears to disappear.
Then,
yes, now we see
yes.
it again.
Then, we have two objectives. First, we have a near real-time automatic QC, and top of this one, we have a delayed mode QC. And there is a gap between delayed mode and automatic QC. We want to reduce the gap by using a machine learning. And in this project, we want to provide uncertainty of a QC. So the human expert can go through a manual quality control from data with higher uncertainty data, and it works more efficient way. In addition, by providing uncertainty, the data user can select the data for their purpose. For example, if the data user prioritize quality over the quantity, then just set the threshold and filter out the data with higher uncertainty data more than the threshold. Then this is our procedure, work procedure. First, we collect the data. Our main data source is a CORA and in-situ tag and World Ocean Database. The CORA and World Ocean Database are fully manually QC controlled, and in-situ tag, it's automatic and manual QC, it's mixed. And our target parameters are temperature, salinity, oxygen, and chlorophyll. And using this data, we want to develop a QC model using a machine learning. Here we have 2 steps. First step, we want to define the sub-region using machine learning. And our main focus is Arctic region. So using a machine learning, we want to divide Arctic region into several sub-regions. And at the second step, we want to develop a QC model for each sub-region. And once we develop a model, we want to test in the Baltic Sea and Mediterranean Sea as well. Then we will deploy the developed model in our data pipeline and share the knowledge with our partner in the Copernicus Institute. So we have obtained about 600,000 profiles from 1980 to 2024. The map shows location of our data. And a lot of data from close to the Norwegian coast and north of Alaska. And the below graph shows number of observation for each profile. Here, observation means measured. So usually, profile have several measurement observations. And a lot of profile have fewer than 50. On the other side, some data have more than 12,000. So for further analysis, I have excluded a profile with fewer than 50 observations. And the left graph shows the number of profiles for each month. In the summertime, we have more data than winter time. Makes sense. And right figure shows the 25, 50, and 75 percentile temperature for each month. And 25 percentile, the lower temperature, is almost always stable. On the other side, the variation of 75 percentile is large. And in the summertime, it's much colder than the winter time, because in summertime, we get more data from a further north area. That's why the temperature is a bit lower than the winter time. And the left graph shows distribution of delayed mode quality flags. Here, 73.8% are good data, and 26% are not flagged. And bad data or probable bad data is just only 0.2%. And we want to detect this 0.2% with a machine learning. So it's very imbalanced data and it's challenging for us. And the right graph shows the distribution for each year. So here, cross year have more unflagged data. This 0 means unflagged data. So cross year have more unflagged data. So I want to introduce how we prepare the sub-region in the Arctic region. And with 0.5 degree grid, we created a bathymetry, distance to the closest coastline, and number of profiles. These 3 parameters we have prepared. And there are some positions which have more than 100 profiles, but we set maximum 100. And for practical purpose, we have created a landmass 01 data as well. And from a temperature data, we create for monthly temperature data. And also we made a 25, 50, and 75 percentiles. So we have prepared 36 temperature parameters, temperature variables. So using these 39 parameters and one landmass, 40 bands, we created NetCDF file and set the projection as a WGS84 and reproject to a North Polar stereographics. The two maps show the example. And upper map shows the temperature of 50 percentile June. And there you can see there are a lot of white, no data positions. So therefore, we have linearly interpolated data and prepare 36 temperature data like this one. And using this 36 temperature and 3 external parameters, we have applied k-means clustering to create a subregion. And we have tested cluster number from 3 to 6. And upper map, it's just the result from k-means directly. And lower map, it's after some image processing, smooth. And I have discussed with oceanographer, it's Vida, and probably 3, 4, or 5 present the oceanographic feature pretty well. So we will use 4 or 5 and develop QC model for each subregion. So this is our future work. We will define the subregions for salinity, oxygen, and chlorophyll with the same manner, and develop QC model using anomaly detection for each subregion. And we want to test the same approach for Baltic and Mediterranean Sea. And we will deploy our proposed model in our data pipeline. And at the end, we want to share the insight and best practice with other in-situ TAC regions. Thank you very much.
Thank you, Oscar, for this overview, for this ambitious and interesting project. Any quick questions from the audience? I see no raised hands. Okay, then I would like to thank all the speakers for this first part of our webinar. And in the agenda now, there is a 15-minute break that you can use to grab some coffee or make a biological break. And then we reconvene at 2:45 for another session of more talks, which will be followed by a discussion session and then a wrap-up. So 15 minutes, and then we reconvene for another session.
I think it's time to start. I think it's time to start the next session. I'm Till Rasmussen from DMI, and I will lead the. I will introduce the speakers, and you'll get 15 minutes each. The first one is Leo Edel from Nansen Center in Norway, and he will talk about reconstruction of the Arctic sea ice from 1992 and until 2010, based on a hybrid machine learning and data assimilation approach. Go ahead, Leo.
Hey. No. Hi. Yeah, I'm Leo. I'm going to present you my work on the postdoc I'm doing at NERSC. I would like to thank my colleagues and the people from ROOS to allow me to present. And today I will talk to you about the reconstruction of Arctic sea thickness based on a hybrid machine learning and data simulation approach. So we'll start with some motivation. The sea thickness is still challenging to observe and usually present high uncertainty. We have significant difference between the various model and observations that we obtain, and there is no consensus or little consensus on the ground truth. And it's only after 2011 that we have the satellite merge product, CI2SMOS, that give us higher precision on the CI thickness, but still the time series that is around 10 years now, it's still too limited for long-term studies and model initialization. So I'm going to show you the CI thickness for one day here from the CI2SMOS product. And here you can see the CI thickness from Topaz, a model, oceanographic model that is coupled with the CIS model that is developed here in Norway. And you can see that the CI thickness is quite different, especially in the Arctic, in the northern part of Greenland. And when we assimilate CI2SMOS into Topaz, so you can see that the CI's thickness is in better agreement. And that is very helpful for us. And so I'm asking you today if we can extrapolate the benefit of data simulation to past period without CI thickness observations. So to do that, in this project, we are having two versions of Topaz. One is a free run without any assimilation, which will be noted FR, and one is a version of Topaz that assimilates CI2SMOS, which we name RA for analysis. And then over those 10 years of simulation, we will train a machine learning algorithm to be able to predict the CI thickness bias into the past. And then we'll obtain a corrected CIS product that we'll evaluate with mooring data and remote sensing. So I'm going to go through all those steps with you now. First, I want to show you the CI thickness bias. So you can see here, average zone Arctic between 2011 and 2022. You can see in purple the satellite products between October and April, and you can see in blue the free run of Topaz. And when we assimilate the satellite observation into Topaz, then you obtain the black curve that you can see now, which matches better the satellite observations. And here you can see the bias, so the difference between the free run and the reanalysis version of Topaz. And you can see that the bias is higher usually at the end of summer when the error have been accumulated over the summer. I'm also going to show you here the spatial distribution of the bias. And you can see that in general, in the free run, we have two thin CIs here in blue, in the central Arctic, close to Greenland, and you have two thick CIs in the Beaufort Gyre in red. So that's the bias average over the Arctic month. But then if we take the monthly differences, we can see that there are variations, but they remain quite small. And we will use this monthly bias as a correction that we'll use as baseline to evaluate the machine learning performance of our model. And I will now show you the methods that we've been using. So on the right, you can see the CI thickness bias, and we will now focus over the period 2014-2022. And to reduce the dimensionality of the problem, we will use the empirical orthogonal function and obtain here 8 principal components. On the left, you can see the spatial distribution of the major component, and on the right, you can see the temporal evolutions. And then for each principal component, we'll develop one train and develop one machine learning model. Each model includes oceanographic input features from the free run of Topaz, as well as the sea ice edge from Anton Korozov. And we also add some atmospheric input features from Error 5. So we are giving those inputs to our machine learning that is based on the long short-term memories, which is a recurrent network. And then we use it to predict one principal component of the CI thickness bias. So here you can see a list of the variables that we've been using, and the main ones are the sea ice thickness, the sea ice concentration, the snow depth on top of the sea ice. And for the atmospheric feature, the more important variable are the air temperature, the pressure, and the total precipitation. And you can keep in mind that depending on the principal component that you are evaluating, each variable have different importance. So I will go through a short evaluation of the machine learning performance. You can see on this graph the bias of the CI thickness between the free run of Topaz and the Topaz with assimilation in the left column. In the middle, you can see the difference between the baseline and the version of Topaz with analysis. And on the right, you can see the difference between the machine learning estimation and the version of Topaz with assimilation. So on the top row, you can see that for the winter month, and at the bottom, you can see that for the summer month. And in both cases, we can see that the baseline show a correct improvement, and the machine learning show even better correction. And that is over the test period between 2011 and 2013. So now that we see that the machine learning show a capability of correction, we can now use it to predict the CI thickness bias backward to 1992. So to do that, we will follow some easy steps. First, we will predict each principal component separately. Then we will reconstruct the CI thickness bias. And then the CI thickness bias will be added to the CI thickness from the free run of Topaz. And then you can see on the right the 2D field for the CI thickness on the 1st January 92, which is the earliest day that we have in this newly corrected dataset. So here you can see the CI thickness average over the Arctic between 92 to 2022. And you can see from the vertical red line and to the left, so we start the prediction in 2011, and then we correct the CI thickness for 20 years. And you can now focus on the free run, the CI thickness from the Topaz free run in blue, and the machine learning correction in orange. And you can see that we are able to extrapolate to earlier time period without removing the trend that is already present in the frame of Topaz, which gives us confidence in the robustness of our prediction. I have also do some validation with satellite observations. So here you can see the CI thickness average over all October month between 2003 to 2007. I will go in the order. We have on the top left, the machine learning version of Topaz. Then you have ISAT1 and VSAT. And on the bottom row, we have the free run of Topaz for references, the baseline correction, and then biomass, which is a commonly used CI thickness product from a model that assimilates several observation datasets. And we can see that there is a good agreement between Topaz machine learning and ISAT1, especially along the Greenland and Canadian archipelagos axis, that we don't see on NVSAT, well, mostly because of the pole hole, but even on the southern part of it, it's a bit less noticeable. And also we don't notice it as strongly in biomass or the other Topaz version. We can also notice that ISAT1 tends to show a thick sea ice in the Barents Sea, close to the sea ice edge that we would maybe not expect. I've also done some validation with in situ measurements, so some upward-looking sonar in the Beaufort dryers and at the North Pole. But for the sake of time today, I will only say that I've done it. And did the same, I did some comparison with other datasets from passive microwave and biomass, and you can see here the monthly CI thickness on the bottom plot with some trends over those 30 years. So we see some good argument with other products, but still some differences that are highlighted actually in the paper that is soon to be published. I'm going to jump to the interpretation of the CI thickness that has been corrected. Here you can see between 92 and 2022, the CI thickness distribution. So for each day, you can see a histogram and the white area not correspond to high occurrence of the CI thickness. And here I have overlaid two blue curves that are actually showing the most occurrence thicknesses. And we can see that from the early 90s, we shift from a bimodal regime to a unimodal regime in the 2020s with a shift around 25. So this is that has been observed in the Farm Strait, but never over the whole Arctic. I have here some average thicknesses over the whole Arctic between 92 and 22, as well as the sea ice volume trends that agrees well with the literatures and show a clear decrease in the sea ice thickness. So earlier today, I asked you about if you could extrapolate the benefit of data assimilation to past periods without sea ice thickness observations. And I hope that I convinced you that with our methods, we can reduce significantly the bias. I've shown you some evaluation with independent data that show a clear improvement compared to the free run of Topaz. And I must highlight that this approach could be implemented for other variables as well as other models. On the right here, you can see a snapshot for 1 day of the animation of the full data set that is available online. So on the left, you can see the CI thickness field, and on the right, you can see the CI's volume. And we see a clear decrease of the CI's volume over the years. So both the animation and the dataset are available online with the paper that has been accepted and is going to be published soon. So I thank you for your attention, and if you have any question, please reach out.
Thank you, Leo. Questions in the audience? It doesn't seem like it.
Mm-hmm.
Yeah, thanks again. And you can always ask in the chat, of course, if you come up with questions later. Next, I would like to welcome Polona Itken from MPI in Norway. She will talk about multi-sensor sea ice data for efficient navigation and climate-relevant data collection along icebreaker transit in the polar regions.
Hi, everybody. Am I coming through?
Yes, you are.
Okay, perfect. So I am new to this group, new to the topic of AI, and I will give a little presentation on the behalf of the Sea Ice group at the Norwegian Polar Institute, where the logo with the crown is coming from, and the flag is a Sami flag, because I would like to honor the International Sami Day, which is today. Sami are the indigenous people of Arctic Scandinavia, so Lirkobavin. I would like to be modest.
Sorry, Polona, we cannot see your presentation properly. Can you please maybe shift to presentation?
Yeah. What do you see my nose? Did you see my nose?
Yes, exactly.
I have to share the other screen. Let me try again. So. Okay. Now you don't have to read my notes. That's great. Is this better?
We cannot see yet the slides.
It claims you're starting to share your screen, but it doesn't show anything but the text.
Yeah, I think it will show up. Cross your fingers. So you don't see anything yet?
No.
Oh man. Just a black screen. Yeah, I see.
But if you want, I can share the presentation from my screen.
Yeah, do that.
Okay.
I think it's better than nothing, and I can just talk. It's not much different. Or it's no, wait. I had some animations. The slides are quite big, so this is why it's probably difficult to share. But if I don't come through in a couple of seconds, maybe you just hijack the screen and share it from you.
Okay, perfect.
Yeah.
Now,
So now it is.
Yes.
we have it.
Right. Yeah, so I'm showing now the overview slide where I admit that I will actually show you what we already do with CIs, but what we would like to do with AI. The main challenge with CIs is that we are working with different scales. Almost everybody talking today was working with a different scale than me. I'm working very locally. I'm working with ice stations, sea ice thickness on the scale from 1 meter to 100 meters, flow ice thickness scales. It is most of the time sub altimeter footprint. And also inside of small scales, even on a meter scale, both media that I have to work with, the snow and sea ice, are complex. They have different kind of, let's say, grain sizes and densities and so on that all interfere with our measurement techniques. Also, we have logistical challenge. There is open water, which is hard to walk on. So also us who really do in situ or saying that they're doing in situ are essentially doing local remote sensing with various kind of devices. Device number one, the old-fashioned device, are our eyes. You won't believe it. It is still done in this way with support of Met Norway, who is hosting or who is maintaining an ice watch system where we share our ice observations. These are visual observations from the ship bridge. For example, you see my feet next to a window there, and I'm looking at the thickness of an overturning block, and I make a note every 3 hours. And on the end of the cruise, like it was last summer in July, August, I made this map of ice thickness, and I also made a map of ice concentration where I looked out of the window and estimated the ice concentration. In addition to this kind of remote sensing, we are also now setting up an electromagnetic induction that we would like to deploy from a ship's bow. This here is now Kronprins Haakon, who has an EM system installed at the bow, and we would like, this was just on one cruise, but we would like to do it now on all cruises, so that we will also have continuous sea ice thickness measurement along the route we navigate. Here is an example of such data compared to my out of the window sea ice thickness data. On the lower part of the map, on the upper part of the map, there is another transect, which is electromagnetic induction based, which was recorded from another ship, which was in the Arctic at the same time as we were there on the Kronprins Haakon. In the background is a sea ice thickness map from Cryosat and SMOS. It's same as Leo has just been showing, from a different year, from a different month. It is the April sea ice thickness, and I subtracted 1 meter to compensate for the summer melt because we were there in July, August. And I tried to compare these thicknesses, just the means, which were kind of off. We were seeing smaller thicknesses than what we would expect. But if we take a look just at the thickest parts, which are then now in the central map, and the thickest parts, the really thickest parts in the more right-hand side, so on the right-hand map, they start to coincide with what we would expect to see. Now finally about the AI, because this is what the workshop is about. We have large amounts of pictures that we never will have time to look at, but we could analyze them into sea ice concentration, like this kind of view. Here's a small short time lapse where we're going through open water and some ice flows of various thicknesses. And you can see how the water is very different. So if I see the difference, the AI should see the difference between the open water and ice cover areas. Same for this kind of side-looking camera. Again, looking at the overturning blocks, just like me, out of the window. There are some ice blocks where we could determine what is ice and what is water and measure the thickness, because the properties of the cameras are known. So I can actually, I know how big is a pixel and I can count the pixels. So this is actually a trivial estimate as long as I can say where the border of the where the interface between the water and the ice or snow is. So we are applying for this kind of projects. We're not doing it yet. I was very inspired by speakers earlier today, where I see that there is a lot of work already being done on the ocean side. So at the ocean side, so sea ice is going to catch up, hopefully. As a summary, I'd like to say that our observations are just one of the, so these observations along the transects from Kronprins Haakon are just one component of the observations that are achievable. We will, of course, still continue with the classical ice station, but then this kind of transects are an opportunity to upscale the measurements, also in collaboration with the airborne observations, which are potentially, or which are definitely even more expensive than what we do from the ships. Finally, in the effort to provide Cowell data to the satellite data. I would like to show this map, which is now in the center of the slide. It hasn't been shown yet today. It's from the Arctic Passion project that Anna, who is our host today, has been talking about. And the standard, the transect we have done last summer on Kronprins Haakon is part of the suggested standard transect in the Atlantic sector distributed observatory. Also, this other ship that had that I have used the data from has been doing one of these standard transects. We hope that we will be able to establish these transects, and that we will also be able to establish standard way of collecting sea ice data along the transects, which will be more than just ice watches, visual observations. So I'm happy to connect with you in this Arctic ROOS, and I hope we can work on this together. Also, I have borrowed the little robot sign from Heather, our host today as well, and using the words of Julien, I hope that our data can contribute to his data-driven model to make it faster, better, and improve the resolution of it. That's all from me for today. Thank you.
Thank you, Pona. Any questions?
Yeah, Heather.
Yeah.
Hi, thanks very much for that overview. Sorry, we have two microphones going on. You have all of these observations primarily in the summer, and you were talking about upscaling. Do you think this could be, for example, a way to help fill the gap with the problems with data coverage from satellites, like the satellite products in the summer? For example, the thickness is more trustworthy in the winter. So do you think AI could help to fill that gap with your data, with using your data?
Yeah, I do believe so. But we don't only have the summer data. There, every now and then we have winter cruises, and the instrument would be the same, and it would be available on that on the winter cruises as well. In fact, in the winter, we should be able to also say something about the snow depths. We would like to install a snow radar next to the EM system, so potentially we will have snow depth. Where again, I mean, the radar retrieval profile is something that is sometimes determined by, which is often now determined by statistics, where again the AI could automatize that kind of detection and improve that kind of detection, so that we will also have snow depth. So there is a lot of space where the AI could be used.
We have more questions. Okay, doesn't sound like it. Thank you, Purna. And we'll move on to Charlotte Durand from ENPC of France. We'll talk about four-dimensional variational data simulation with the CI's thickness simulator.
Yes. Can you hear me?
Yes.
Okay, perfect. First of all, thank you very much for having me here this afternoon. So I'm Charlotte Durand, and I just finished my PhD as a part of the SAICIP project, so funded by Schmidt Sciences at École des Ponts. And so now I'm just starting a postdoc in Grenoble. But today I'm going to talk to you about the work I have been doing during the PhD, which is a 4D VAR data simulation scheme with a CI thickness emulator. And I would like to acknowledge all of my co-authors and team in Paris, Bergen, and Grenoble. So I'm working with NextSim, which is a Lagrangian CIS model, so with the BBM rheology. And Guillaume Boutin has coupled this CIS model with an ocean model, OPA, to make a pretty high resolution simulation from 95 to 2018. And this simulation output is the dataset on which I'm going to base all of my work. And the idea was, is it possible to replace the physical model, so NextSim, by a neural network to predict the next state of the system? And here I'm going to focus on CI thickness. So if I give to the neural network the CI thickness at a given time, is it possible to give me the CI thickness in the future? And in order to do so, we decided to focus on predicting the 12 hours dynamics. So instead of predicting the full state afterwards, we only try to predict the evolution of the CI thickness during 12 hours. So in order to get an emulator, we need to have an architecture for the neural network. So we decided to stay on a pretty classical U-Net-based architecture. One nice thing about this neural network is that it uses partial convolution. So it just means that a land mask is embedded into the convolution architecture. So the convolution knows if there is land, and in this case, it's not going to learn anything on those grid cells, and it's only going to focus on the ocean. And we're also going to add some atmospheric forcing, so additional information that we give as inputs of the neural network. So the velocities, the wind velocities, and the 2-meter temperature. Plus the CI thickness, obviously, of Nexim. So the results that I'm showing you here are done for a deterministic neural network using the mean square error for the loss during the optimization. And we add a constraint, a physical constraint during the optimization to minimize the bias error. So we also estimate the total amount of CI thickness and we reduce it to get a really nice bias for our model. And once the neural network is trained, we are going to move into the surrogate phase. And so we're going to initiate a trajectory by taking a Nexim state, and then we're going to apply it over and over again, and then evaluate with different metrics the results of the emulator. So for example, if we look at the RMSE, we see that we have a pretty good RMSE on the full Arctic, and we beat the persistence by between 30 and 40%, depending on the lead times, which is already a good fit because, as you may know, persistence is already a good baseline for Arctic-wide CI thickness modeling. And if we look at a full year forecast, so I initialized a forecast on the 1st of January, and then I applied the emulator 700 times. And this is what you can see. So on the left is Nexim, the CX model, and on the right, the neural network. So we can see several things on these videos. First of all, we have a good advection large-scale dynamics of the CI thickness. And we also have a good representation of the thermodynamics because it correctly gets the melting period, and it also gets the refreezing period pretty nicely. So this is really due to the temperature forcing that we give to the neural network as inputs. But what you can also see, and this is something that Julien already mentioned during his presentation, is the smoothing effect. So we are losing the fine scale dynamics. So this is due to the fact that our neural network is deterministic and learning, so it's optimized with the mean square error. And if you use MSE to minimize, the best solution is to average the fields, which is going to give this smoothing of the CI thickness. So we could quantify this smoothing with power spectral density. And so this is something with deterministic neural network that is going to be difficult to fight. It will be really difficult to get less smooth fields, but we tried. So for example, by adding PSD loss during training, so it means that we are learning, we compute the power spectral density for every examples during the training, and then we try to match the PSD of the output of the neural network with the PSD of the truth, which gives some really slight improvement in terms of PSD, as you can see on the right graph, but there is a huge computation cost due to computing the PSD for every iteration during training. But in any case, this emulator is in inference stage really fast because it takes less than 1 minute to run a 1-year forecast on one pretty big GPU, which is really one of the strengths of the emulator and data-driven model in general. So one of the questions that came afterwards was, is it possible to do data assimilation with this emulator? So in CIS modeling in general, so ensemble methods are used, because we do not have the adjoint of the CIS model. But we have to remember that those data assimilation methods are pretty expensive because we have to run the model, the physical model for each member. And so we wanted to focus on variational methods, which require the adjoint of the model. But this is nice because with neural networks, we get the adjoint for free with automatic differentiation. Plus, we can see that this data assimilation scheme is pretty fast because everything is quick to run with the emulator. So just in a nutshell, the 4D principle. So the idea is that we're going to take a window, a data assimilation window, and in this window, we are going to compute a cost function that is going to look at the mismatch between so the initial state of the system and an a priori we have of the state of the system. And then we're going to propagate our physical state into time with the model. And we're going to compare at some times, so in the future, observations with the state of the system at this time. And when we're going to get the analysis, we will have to minimize so this cost function using variational methods, meaning requiring the gradient and the adjoint of the model. So we tried some first of all twin experiments for the validation, meaning using synthetic observations, so adding noise into the truth. And we looked at two different methods for the 4D VAR. So for the estimation of the B matrix, so the background covariance matrix. So either a diagonal B matrix or we try to project everything onto the EOF, so the empirical orthogonal functions, which in this case bring a small improvement. So if we look at the results on the right, it's the forecast RMSE. So this forecast is done at the end of the analysis of the data assimilation. And the black line represents the emulator free run. And both the gray and the purple lines represent of our 4D VAR forecast. So we see that we already have a strong improvement compared to the free run. And actually, if we compare our forecast with what would be the best possible solution, so starting the emulator at the beginning of the forecast with the perfect initial conditions, we see that our RMSE is even slightly better at the end than this perfect initial condition run. So this was our first proof of concept that we can use our CI emulator for 4D VAR. And so then we tried to move to real observations. So the idea is to assimilate CS2 smooth, so daily observations with 8 days data assimilation windows. And once we've done this analysis during those 8 days, we're going to do a 9 days forecast using ECMWF forecast, atmospheric forecast input into the neural network. And at the end of this forecast, we're going to compare our system with Nexsim F, which is the currently operational Nexsim, so data simulation methods using Nexsim, which is run, which was introduced by Tim Williams and is available on Copernicus. And if we look at the results, we can see that we have results that are pretty consistent with Nexsim F. And so in those plots, what we want to compare is the blue dots with the end of the purple dashed line. So in terms of RMSE, we are pretty close. We are slightly better at the end, actually, of the data assimilation cycles and pretty worse at the beginning, but we have some difficulties explaining this. And if we look at the bias, what we see is that we have a really nice correction of our emulator, which is biased, obviously, and so we really get a nice correction with our 4D techniques. So there is some, we still have some stuff that could be improved. So for example, as you've seen before, the emulator tends to smooth the fields, but the observations are really smooth. So we obtain a smooth analysis because we have smooth observation and a smooth model. So this is something we would still like to improve. And so just to conclude, I've just shown you a CI sickness emulator, which is really fast, but tends to smooth out the fields. Yet it can be used in variational data simulation methods with results that are close to current operational systems. So thank you very much for your attention. And if you have any question, please feel free to ask.
So are there any questions in the audience? Thank you, Charlotte, by the way, but let's give them. Doesn't seem like. Yeah. So where's my mouse? Okay, then we'll move on to the next one. Andrew McDonald from BAS, UK, will talk about short-term high-resolution CIS forecasting with a diffusion model and samples.
Hello, everyone. Let's see. Oops, let me go back to the start of my talk. Let's see. Screen sharing working all right? I'll take it as a yes.
It's working.
Cool, wonderful. Good to meet everyone. I'm seeing a lot of familiar faces on the call, which is always good to reconnect. So thanks for coming out today, and thanks to the organizers for putting this on. The talks so far have been really, really interesting, and actually have answered a lot of my own questions about some papers and things that are out there today. So really good stuff. I'll be talking about some recent developments using diffusion models from the computer vision literature to do CIS forecasting here at BAS, building on the IceNet project, and hopefully get some thoughts on where I can take this next. So we'll go ahead and jump in. I think I'll start with a bit of motivation, but I think this crowd probably knows it better than any why we need high resolution CIS forecasts. The previous talks have touched on this really nicely, and I'm excited to see some of the products that are coming out, down to kilometer scale and sub-kilometer scale. But really, at the British Antarctic Survey, we're motivated by in-ice navigation with our research vessel, the Sir David Attenborough. And so the AI lab where I'm doing my PhD here at BAS works very closely with our operations team and with the folks navigating in ice on the ship. And so they're always keen to have up-to-date real-time information on not only the present state of sea ice, but also how sea ice is changing. And so that's sort of the motivation behind a lot of this. And there's some downstream products that are really exciting here at BAS that are using these forecasts and real-time observations to plan more efficient routes, both to save time, but also energy and carbon. So that's sort of why I'm doing what I'm doing. We also have a postdoc in our group working on understanding how migration patterns of caribou in the Canadian Arctic are affected by sea ice concentration, and then trying to forecast sort of migration behaviors based on forecasted sea ice concentration to better inform conservation operations and sort of define no shipping zones and things with notices to mariners in collaboration with the Nunavut government. So a lot of cool things going on, but I want to talk a little bit more about diffusion and kind of the problem domain I'm working with. So just to set the scene, I'm looking at a region actually in the Antarctic here, but I'll circle it back to the Arctic at the end of the talk. So I'll try to keep it relevant. But this region is one of the most heavily traveled by our ship. So in the top right of this domain is where our research station Rothera is. And there's a really defined seasonal cycle of sea ice growing and then receding. And the process of that breakup is really important to our navigators as they're planning to do resupplies and things to the station. So this is sort of the test bed on which I've been developing my diffusion model forecasts. But again, at the end of the talk, I'll bring it back to the Arctic. And that's actually where I'm sort of experimenting with now, a region in the European Arctic for writing this all up into a paper. So yeah, we'll get there. Just to set the scene a bit with the original IceNet. So I mentioned this project is kind of building on IceNet. What is IceNet? It was all sort of started with a paper in 2021 published by Tom Anderson. He was, the team there developed a deep learning based CS forecasting system using ERA5 reanalysis meteorological variables and then OCSAF 25 kilometer sea ice concentration products, and did sort of subseasonal to seasonal forecasting at monthly timescales out to 6 months in the future. And so this sort of the headline result from it, and I'll say this is a team effort that's been continuing and has been going on. But the headline result from that first paper was that IceNet was able to outperform the SEAS5 model from ECMWF for subseasonal to seasonal forecasting. And in particular, did really well in sort of the summer months when predictability drops off. So that was an exciting result. But this has been under development for a while, and there's been a lot of changes. I think the motivation to bring in diffusion models, and where I'm working on this sort of short-term high resolution stuff, is that one of the issues we saw with IceNet, and which has been mentioned in a few of the other talks, is that with these deterministic machine learning models, we often get really blurry outputs that are sort of physically inconsistent and don't realistically represent the ice edge, which is of course a really important feature for mariners, but also for biology and other processes. So the hope with diffusion here is that we can more sort of sensibly represent both the ice edge, but also better characterize the sort of uncertainty in the ice edge and the CS concentration distribution more generally. And so a quick primer on diffusion. It's, again, this method that's sort of come out of computer vision. So a lot of the state-of-the-art image generation models that you may have played with, Imagen, I don't actually know what models under the hood of ChatGPT these days, but all those sort of image generation models are built on this diffusion backbone, which essentially takes an image from some kind of data set, adds noise to it, and then trains the model to predict the noise that was added so as to be able to denoise an image. And then the idea is that once you've trained this model, you can take a noise, a sort of batch of input noise, and then denoise it into an image that is representative of one from the data set. But of course, we can consider sea ice maps as images, and then do this same process on environmental fields of any sort, really. And so this is just sort of a toy example here. Again, this isn't the domain I'm dealing with, but in the Antarctic, if we train a model, we can get something that looks like this just to show the denoising process. So the sort of test bed that I'll dive into here again is this region around Rothera in the Southern Ocean, or in the Bellingshausen Sea off the Antarctic Peninsula. And I'm working here with AMSR2 data from Uni Bremen, so the 6.25 kilometer product there. And I know, again, there's been some new products mentioned in the earlier talks, so I'm really excited to maybe try some of those out. But for now, this is kind of what we've been working with. So I've just sort of keep computational requirements light, and also to just kind of simplify the engineering for the start. I'm looking at just this 128 by 128 pixel region, so 800 by 800 kilometers. And I've formulated the problem actually as an autoregressive forecasting problem, sort of inspired by the success of GenCast, which some of you might be familiar with. This is the recent paper from Google DeepMind, which was using diffusion models for weather forecasting. And so that paper, and then what I've done here is treats sort of the forecasting problem as a order 2 Markov process. So if you have a model that takes in the previous 2 days, in this case, of CS concentration, so the previous 2 states, then train it to predict the next day, we sort of assume that captures all the information in the process. So we should be able to do conditional prediction of the next day on the previous 2 days. And so then I also feed in the climatological average of CS concentration for the next day and sine and cosine embeddings in a land mask to give the model some more contextual information, but keep the actual predictors and target very simple here, such that if we are able to train this model successfully, then we can, at test time, basically feed the predictions back into the model and roll out to an arbitrarily long lead time. And I'll show some results here, which I'm quite excited about, that show I'm able to, with this trained model, roll out to 30 days without the model sort of blowing up. Now, the accuracy at those longer lead times is questionable, and I'm working on evaluating that. But these long rollouts are possible and stable at longer lead times, which is exciting. Yeah, I've trained it on this 2013 to 2019 window here, validated 2020, and then have cut my testing now for 2021, just to sort of not stray into the sort of changes in Antarctic CS that we've seen. But just to show, I guess, to motivate a bit to the, why I'm doing it this way. One advantage of diffusion models that I should have probably mentioned earlier is that they sort of naturally admit ensemble forecasts, in that you feed in noise to initialize your forecast. And so by feeding in different initial noise states, you can actually get slightly different forecasts from the model, from a single trained model. And so here I have 32 different ensemble members, which are all initiated from slightly different noise samples. And as we roll out, you can see each of them sort of exhibits different dynamics. So there's some ensemble members where we see a really low ice regime, where the ice recedes. And then there's others where we see a higher ice regime. And for reference, this is in the Austral winter in September, but sort of going into the melt season in the Antarctic. So pretty cool sample diversity from this diffusion model. And if we want to actually compare against the ground truth, this is how, on the left here, the ground truth evolves over that time. The ensemble mean among those 32 members, does a decent job, I guess, of capturing that. And you can see the standard deviation on the right there. The ensemble sort of can capture this uncertainty around the ice edge as well. And actually, a better way of looking at that is to look at these sort of spaghetti plots, if you will, of the ice edge. And it's exciting to see that as the time evolves, the sort of spread among the ensemble member ice edges spreads out, as one would expect, but largely captures the ground truth ice edge, which is the magenta line there. And again, this is rolling out 30 days, and it's pretty remarkable, I think, that it remains stable over 30 days, though it's only been trained on 1 day ahead prediction at a time. So I think that's pretty exciting. We can look at another way sort of to characterize, I guess, the quality, if you will, of the output forecasts is to look at the power spectral distribution. So we can see as we roll out that the power spectrum of each ensemble member largely follows that of the ground truth. And so in particular, some of these high resolution features, which would have high wave numbers, so towards the right of this plot, we can see the ensemble members are doing a good job of maintaining signal power at those really high spatial frequencies. So in other words, it looks like these ensemble members are capturing some of the really small scale features in the domain, which is exciting. If we can also look at more conventional things, just like RMSE, and I'll show binary accuracy on the next slide. And I've compared this against some really simple baselines here, just persistence, climatology, and then the ensemble mean, and actually, at least at the first 5 days, the models are performing pretty well, but even out to longer lead times, they still don't exactly blow up. And binary accuracy, it's a similar story, but it stays pretty similar. And this takes me to the connection to the Arctic here. So as you know, I sort of started my experiments there in the Antarctic, motivated by this application for operational use at BAS. But as I kind of work towards the first paper on all of this, I've been trying to look at what other regional sea ice forecasting models are out there for short-term and high-resolution forecasts. And actually, a lot of the ones that have been mentioned today have been on my radar. So I'm looking into comparing and sort of benchmarking these forecasts against the Barents 2.5 model, the NextSim model, and then also the AICE model from Met Norway. And so I'm still working on training the new model in the Arctic in this new domain, which is why I was showing the results from the Antarctic, just because I've gotten that all running. But the sort of next stage of this project will be to train the diffusion model in this domain, compare against some of these physical baselines and also the AICE baseline. And if you have any other baselines you think I should look at, send me an email. My email is on the bottom of these slides. But yeah, that's kind of the next stage. So, I have a lot of ideas, I guess, on how to improve things. I think, better data, I said here, I think eventually training on some of these newer 1 kilometer and even 500 meter products that were shown earlier could be quite exciting. I know there's a lot of issues with sort of the raw AMSR data from Uni Bremen, so looking into that. Metrics, I still have yet to implement some things like integrated ice edge error, but I'm planning definitely to look on that. I know that's, and then some other conventional metrics from the literature. So working on that, but yeah, I think I might leave it there and save a couple minutes for questions. But I will just say thank you everyone for your attention, and yeah, please do reach out if you have any kind of follow-up that you'd like to be in touch about.
Thank you, Andrew. Are there questions? Okay. It doesn't seem like it. Yeah, but thanks again for spinning the globe to the other side. And then we move on to the last speaker of today, Lorenzo Zampieri from the European Center for Weather Forecasting. He will talk about how they move towards an artificial intelligence Earth system model. The floor is yours.
Yes. Hi, everyone. Thank you, Till, for the introduction. Can you see my slides fine?
Yes.
Okay, perfect. Thank you. Yes, so as Till said, my name is Lorenzo Zampieri. I work at ECWS. And today I will explain you how we are planning to expand our machine learning efforts that started in the atmosphere to the other system components, including the ocean and the sea ice. So let's start. You need to be patient with me. I need, since we do mostly weather forecasting, I need to start from the atmosphere. And yeah, I just want to spend the slide on this machine learning revolution that we have seen in weather predictions. So I think it's fair to say that by now ML models outperform traditional numerical weather prediction system, both for deterministic and probabilistic medium range weather forecasts. Once trained, ML models are several orders of magnitude faster and more energy efficient, as we heard many times today. These ML models rely on reanalysis or also directly on observations. And also these new techniques brought new players to the table. We know that Google recently operationalized their GenCast and GraphCast products, and NVIDIA is also developing forecasts. And yeah, basically you can see that for key metrics such as humidity temperature at the medium range, our AIFS model substantially outperformed the traditional numerical model IFS. So how does AIFS, or I would say in general, machine learning model for weather works? So the AI model learns from several years of reanalysis, in our case, RFIs. And it basically learns two-step into the future from analysis state to analysis state. And these analysis state are basically the key. They are observationally constrained and they have a high quality representation of the atmosphere. Once this is learned, basically for forecasting, we autoregressively step the trained models 6 hours into the future, or depending on the time step that we learned. And basically we have our weather forecast. Yeah. Now, the question is how this technique generalizes to other Earth system components. Thankfully, Destination Earth funded activities to explore this avenue. And in particular, at TCNWF, we are developing specialized ML emulators for other major Earth system model components. In particular, the ocean waves, sea ice, hydrology, and land. And ultimately, the goal is to obtain a comprehensive ML description of the Earth system for environmental predictions at different time scale. And yeah, my focus is, of course, on ocean waves and sea ice with particular attention to the polar regions. So the current questions that I partially will try to address in this presentation are the following. So do current ML techniques generalize to the marine component? What are the skills of these data-driven forecasts? How do we combine several ML models? So the concept of coupling in these new architectures. And yeah, are forecasts stable and physically sound? Yeah, just before I start showing some results, I want to mention that this is, of course, an effort that goes beyond me, and I'm part of a fantastic group of people working on this project. So let's start with some results. Here you can see a model of the sea ice and surface ocean together. This is an ML emulator, and as you can see here, we have an atmosphere that forces ML ocean and sea ice models. So we could say that this is an OMIP-like configuration. We trained this model on RS6, which is our newest ocean reanalysis over the period 2005 to 2021, with a 24-hour time step, a quarter of a degree resolution approximately. And here I'm showing the model integration over 2022, so just outside the training period, and you are seeing basically the surface temperature together with the sea ice concentration. So you can already see that at first glance, this simulation looks kind of realistic. We definitely have a seasonal cycle. We have features that we recognize. We have a convincing evolution of the ice edge that is in good agreement with the Ozusako observations. We also have eddies and currents in the ocean that, yeah, give us promising. I think overall the results are promising, but of course we need to do a much more careful evaluation in the future. So how does this emulator work? We start from a set of 2D prognostic variables, in red the oceanic variables. So you see the surface temperature, you see the currents, the salinity of the surface, and the elevation, the sea surface height, and a set of sea ice variables. We have the typical set of forcings that we use in OMIP simulation from the atmosphere, from RF5. And then also the model is aware of the land sea mask. The time step is 24-hour, and this means that the model knows the state at T minus 24, T, and it predicts what happens at T plus 24 in a kind of iterative way. So you can see how the prediction becomes the new input state. During training, the model actually learns from all the states every 6 hours, but then at inference time, the time step is 24-hour, but the same model can start at different time of the day. In terms of sea ice performances, like these are just preliminary analysis, but they look pretty convincing, at least for one of the few architectures that we are testing. Here you can see like the solid line is the RS6 analysis, very close to the observations. In the dashed and dotted line, we have the two machine learning architecture that we tested, the swing transformer and the graph transformer. And yeah, you can see the comparable simulation, which starts from the same initial conditions and runs for 1 year under the same forcings. And you can see that in general, the swing transformer model, which we also use for weather forecasting, is very close to the analysis. And it's interesting to see that, for example, in the Southern Ocean at the end of 2022, when we had an anomalous retreat of the sea ice, the machine learning model captured that, whereas NEMO went, I would say, a bit more in a climatological direction. And yeah, it's interesting to notice that with the 2D model of basically just of the surface, we managed to be, let's say, comparable to a 3D established ocean model like NEMO. But I think the key and what you should keep in mind is that we are learning from a dataset, ROS6, which is produced by a 3D model. So we basically learned the 3D impact of the ocean over the surface. And this implicit representation of model components come back often, I think, in our work in recent months. For example, here you can see a model configuration where we have an atmospheric model plus wave all trained together in one model. And you can see that an animation of the forecast with sea survey site. And you see, of course, the waves are not penetrating into sea ice, they are attenuated. And by just learning the wave structure, the model learned how the sea ice edge moves. So in a way, we have already a representation of the sea ice model when we include the waves in our forecasts. And yeah, I just want to show another example. This is a very different project that we are working on at TCNWF. It's graph DOP, so direct observation prediction. And the idea is to predict from the observations the future observations, so completely bypassing the analysis. And of course, on the AMSR2 channel that we can model with this graph DOP, we see a strong imprint of the sea ice. And you can see that basically the model at day 10 learned to freeze the ice accordingly. So kind of combining information from the atmosphere and like basically producing like the behavior that we also have in our sea ice models. More details on this can be found in this preprint, but I thought it's curious for this crowd. Now, a bit about coupling strategy. Of course, we can develop a lot of separate models as we do with numerical models, and then bring them together as we do traditionally, so exchanging fields. Or we can also do joint models. So we bring all the components together, we train them together, and we basically bypass the coupling. And I think both strategies, and actually everything in between, so there is a lot of flexibility with these new techniques. And both strategies have positive and negative aspects. In this case, we have a fully differentiable system, and all the components can benefit from, can build correlations with each other. In this first case, so the traditional coupled one, we kind of decide where to put the interfaces and what is exchanged from one component to the other, which might also be interesting. And also it allows a bit more flexibility with the training data set. And very preliminary, the results that we have, so this is just a recent result, just with one forecast. So we managed to implement these two strategies and to test them. And it looks like at first glance, the results are comparable, which I think it will be interesting to do ablation studies in the future. But yeah, it's encouraging, and But yeah, more investigation is definitely needed. I also just want to close the presentation by mentioning that with this new type of model, we also need to do some reflections on the observations that we can use and that are important. So in traditional model, for example, in situ observations are used for process understanding and parameterization development. With these AI models, what comes from in situ observation is a bit more difficult to use, also because we struggle to produce fluxes. Our models, AI models, are very good at simulating state variables, but we cannot really do fluxes. Or coming back to the discussion that Greg Smith had at the beginning, in the chat, we cannot do pressure, for example. So we need to be aware of this, and within PCAPS, which is the polar coupled analysis and prediction for services project, we are thinking about these aspects. So we established a task team called ROOS, which is observational requirement in the context of AI prediction system, and it's gearing up in these weeks. Yes, with this, I thank you for your time, and I'm happy to take questions.
Thank you, Lorenzo. There's one chat from Julian. I don't know if you want to, I can read it up. You're using transformer and graph-based models, given that most of the processes are, 12 hours, are local in space. Do you think that good old UNet could also be used, or have you tried it?
I think in principle, yes, it could be used. We are using a graph architecture because it allows us a bit more flexibility with like the type of data set that we can encode and decode, and also in the way we build the attention window. So we can do, for example, like we can apply different attention strategies. But yeah, probably it will work also with a more regular UNet. Yeah.
Try again. Are there other questions to Lorenzo?
I've seen a hand raise, but maybe I can start to me for me to monitor the chat right now.
The last one in the chat was someone saying black screen to Polonia's presentation, I believe.
I have a question.
Okay.
If that's okay. When you talk about coupling, I'm not so familiar with that, but do you have a feel for which coupling components are the most important and which ones are more second?
Yeah, so I think not yet, but we might have an answer soon. So the result I showed here, maybe I was too quick, but what we are trying to couple here was simply the ocean, the surface ocean and sea ice with the atmosphere, and we were coupling the variables that are typically coupled in numerical models. So we were trying to replicate what happens in the traditional sense of coupling. And it looks like we can basically, like with this information that we exchange, which from the ocean to the atmosphere is basically the SST and the sea ice concentration, we can get a very similar result compared with a model that that fully sees the other component, that can establish potentially correlations also between the sea ice and the stratosphere. So probably we are already exchanging most of what's needed. But yeah, ablation studies will be interesting in this respect. And I think more results are coming, probably more robust results. This is just the very first attempt.
Thank you.
More questions?
Yun Shi has the question.
Okay. Please, Jun.
Yeah. Hi, thank you, Lorenzo, for your presentation. I have a question on the 3D ocean forecast. Mercator Ocean, like they have GlowNet. Also, have you worked with them, or how about these the ocean AI forecasts will be developed in the future?
Yeah, we are actually I didn't mention it here. Let me go back a bit. So Rachel in our group is leading the efforts to also extend kind of a very similar architecture and approach to the 3D ocean. So we are developing a 3D ocean model also based on RS6 at the moment. And I think results will come over the next months. But we are going in the same direction. So we are also exploring the 3D part.
Okay, so for the 3D ocean, it's a similar strategy to make the forecast as for the weather part.
Yeah, I think it will be interesting probably for different timescales. So we know that in a way we're learning the atmospheric forecast from Era 5, which already has a representation of the surface ocean and the sea ice. So probably including a 3D ocean at the medium range will not bring huge benefits. But then we expect that the longer the time scale, so at the subseasonal, at the seasonal time scale, having a representation of the explicit representation of the 3D ocean will become more and more important. And probably in this respect, we will also investigate probabilistic approaches, or for example, diffusion models or the CRPS approach that we are developing for our ensemble. Because at longer time scales, we also need probabilistic forecasts and not just a deterministic model as I presented today.
Okay, thanks a lot.
Okay, I think we should move on to the discussion part. It's a bit following the same track as we're doing now, but thank you, Lorenzo, for your presentation. And Anna, I'm not sure who's going to take over now, because I don't think that Manuel is here.
No, but Vida will. Yeah.
Okay. I will be standing for Manuel.
We had a question from Neria as well. To not miss out.
Yeah, so I think since we have time, I think Jari should be able to bring his question. Jari?
All right, thanks, Vida. So thank you for all speakers. It has been really great day and afternoon looking about this progress. And I have to admit that I'm an old school man, and I have never believed on the machine learning thing. So for me, I have to think that machine learning is that one can utilize the statistical methods to make and visually similar kind of product, what you can do the models. So maybe this is also good for the discussion part. So what I really, of course, I think that my mind has changed. But I would like to ask a couple of the basic questions from all the speakers today. First is about the conservation. When we are talking about the physical models, we are always concerned about the conservation of mass and momentum, energy. So how the statistical models or the machine learning models, in particular when you are having for the Earth system models, how conservative they are in terms of energy? Then it's about the machine learning method are always used in the training data. When we have the training data, then of course the training data is limited. And when we are training any kind of algorithm for training data, how well the algorithm is for the extrapolation? If you think about the physical models. Physical models can always use for some new systems. We have if we believe on the physical principles and physical models, we can make a scenarios like increase the CO2 in atmosphere. We don't have the data on the future climate, but within the models, we can estimate what kind of extremes there are in the future when the atmospheric CO2 is changing. Or for the ocean, we can do the function like in a very practical application. If we have built an offshore wind farm, a bridge on sea, on ocean, any kind of construction, then with the physical model, we can calculate it how this kind of structures are changing the current. Would the machine learning methods would be very attractive of doing such kind of things too, but how they can apply it in a problem where there doesn't exist any kind of measurement. Maybe these are a couple of things which I like to hear about your opinion. Thanks.
Thank you, Jari, for these very good and fundamental questions that go straight to the core of the aim and motivation behind this webinar, to discuss what it can be used for and what it might not be used for. So with the questions from Jari, is there anyone in the audience or from the speakers that would like to start the discussion?
Maybe I can give my take on this.
Yeah,
I think they are two very good points that come up often, and I don't have a good answer. For the first part about the conservation, so first of all, it's really application dependent. So in our case, at ECWF, for example, for forecasting, also our numerical model, so the traditional one, doesn't have perfect conservation of energy and momentum because of its numerical formulation. And this is acceptable for us because we don't need conservation at the medium range or at subseasonal time scale. And of course, when we train the machine learning model on a reanalysis that does data assimilation, we cannot expect conservation just to magically appear. There are efforts to build conservation in the loss function of these models. But yeah, I think it's still an open question. But I would say for certain type of applications, we don't really probably need a perfect conservation, and these models can still be useful. The question about the extrapolation part, yeah, it's also a very good one. And I think for now, probably we see that definitely we can extrapolate also, like with a training period that covers many years, we can do weather forecasting also at present day when we have a climate change signal. And the question of doing climate simulation with machine learning, I think it's very, very open, and it will be exciting to see what happens in the next years. But yeah, I don't have a good answer to that. But yeah, a bit of extrapolation, I think it's possible. Yeah, already now.
Thank you. Are there others who have any comments on these kind of questions? No one who wants to add some comments on a straight on? Not surprising, maybe these are fundamental questions, but I think these are very important also to acknowledge and be aware of. That when we apply these kind of models into the future, when things have changed, and there might be events that have not been covered or captured in the past, in the history, and how do you model that into the future or extrapolate? And it's also important because these might be the events that we really want to know about, the extreme events or the sort of space where you can expect events to occur. How large amplitudes will there be and so on. which is what is important to know about in the future, to scale things according to the amplitudes that you can expect in the systems. So if there are no other comments to that currently, I think we have a set of questions also from our side. I don't know if you, Heather, have a slide that we can bring up with some other questions, which is also relevant. So first, I would like to thank all the speakers for a lot of interesting talks. Very inspiring to see all the applications. And it clearly is a lot of evolution going on. And these new tools will give us capabilities that we have not had before. So a lot of interesting things will be happening and lots of possibilities that we will have in the future. So our questions goes along the lines of how does AI improve our forecasting ability? And what do you think the main use is already now, and what do you foresee in the coming 5 years? And some of you have touched upon this, the limitations of AI for now, and that will still remain in 5 years. And what can AI not help us with, at least not today? If there are any further comments in addition to what we have already seen in presentations, that would be very useful and very interesting to hear your take on. And I especially challenge the presenters, but of course others in the audience are also free to comment on this. So if you have any comments to any one of these questions or all of them, please raise your hand and we can have a bit of discussion on that. And we also encourage people to also say if there are any challenges that you have encountered that you might want to share your experiences with. What did not work, for instance, or experience on whether there are sufficient data or whether there are limitations in the data, for instance, in the coverage, and also on your impacts on efficiency or quality of the products and so on. I know some of you have touched upon this already, but if you can elaborate, if you want to share those experiences, would be interesting.
I can comment if I can't find the raise hand function. I'm sorry.
Okay, yeah, please go ahead.
But I can speak from the user perspective, from the operational ICE service perspective. So I think that we foresee AI is going to be certainly the workhorse to allow us to use a lot of the combination of sensors to potentially take away some of the work from the analysts, so they can actually do less manual ICE charting and focus more on the analysis. So with this, we could potentially use the AI to automate some areas that are consistent throughout the year. So for example, areas, older ice and areas in the high Arctic, but then we would plan to have a semi-automated service in the near future, even with the new satellites coming out. I think even if we do have a lot more availability of the more high resolution satellites and new synthetic aperture radar frequencies, then it's going to allow us to do a lot better mapping. We can put out more ice concentration charts. We can also expand on how often we can provide sea ice type on a routine basis. And hopefully this can really help with a lot of the forecasts. But I think that all the sensors in the microwave, active or passive, are still going to have the same limitations. So it's going to require this level of QC oversight. But at least this will allow us to really make use of a lot of the current suite of sensors and the future suite of sensors. And this right now is a big issue that we have, is that we're really underusing this. And we're not taking full advantage of we have. So I think, and I want to quote from a colleague of mine from the UK Met Office, that we just need to, we know that none of these are forecasts or automated products are maybe going to be perfect, but as long as we understand how we can use them and how we can't use them, then I think this is going to be a huge benefit for us. So the limitation is always going to be the snow on sea ice. And I'm not quite sure what types of sensors are going to allow us to address this and overcome that and to have full automation. But I think we are seeing a lot of improvement. I do see that we're still trying to evaluate whether or not these sensors or the AI is going to pick up on the extreme events. What we see is that previous knowledge of the history of the ice, we can't really apply it to current and future conditions because it's changing so often. And I think that this is going to be a big challenge.
Thank you. Very good inputs. And it's a very good point that AI can help us to sort of better leverage the observations and sensors we actually have, because especially in the Arctic, this is the case that observations are scarce. So if we can squeeze more out of what we have, that's very, very valuable. So that's a very good point.
But ideally, like I would say, because the ice charts, yes, they're not they're old, they're not useful for navigation on a tactical level every day, but in the absence of observations, they are a very good ground truth. We want to maintain the quality of the archive so that we also in the future we're not putting AI into, like AI is not training from AI. Like there has to be a quality control input on that.
Yeah. Other comments?
I think I guess I'd just agree with that I think I'm particularly excited about sort of the potential for multimodal applications and sort of, I guess, fusing different data sources that are sort of being underutilized. So I think like in practice, I see there's a lot of data, for instance, that gets collected on the British Antarctic Survey ship. And of course, all these polar vessels collect all this information. And I know some of it gets passed into models somewhere, but I think there's, at least as far as I see it, and like for CS observations and things, there's a lot of, easy wins maybe to be had there, but it's just a matter of connecting the dots and sort of pulling it all together. So I guess the background for this thought is that one of my collaborators here in Cambridge was involved with this project called Aardvark Weather, where they were doing sort of like end-to-end weather forecasting with machine learning. So instead of training on ERA5, they did train on ERA5, but as opposed to just sort of learning this forecasting model of ERA5 to ERA5, they tried to go sort of one step further and take observations from aircraft, from radiosondes, from scatterometers, and sort of like go back to sort of the raw data and then learn sort of to observations from that. And so I think in the Arctic space, or the sea ice space, there's maybe room for that. So leveraging buoy data, leveraging some of this data that's maybe not, I guess, less remote sensing, but yeah, combining in situ and remote sensing and all of these things, I think in a fusion, something I'm really excited about.
Yeah, good point. Any others who wants to bring some comments?
Bologna put one up in the chat.
Yeah.
Yeah, I did, and I can actually ask this, so that you don't have to read it. So it is kind of obvious, and hope and I'm not wrong, is that most of us are AI method users. None of us developed a new method. So we're not AI researchers, we are AI users for research we would like to do with the data after we have used the method, right? This certainly applies to me. And I'm also quite old. I'm not an early career researcher anymore. Most of the presenters today were. This was really fun to listen, actually. I'm very happy for that. So I did not cover this at school at any point, right? But it is here, and some of my tasks are so simple that I was even told that I can't get anybody to do a master thesis on this because it is so trivial. My problems are trivial, but when I look at it, like, how am I going to do this? It sounds like, oof, right? So it is. It feels like it's this getting out of the couch challenge. It's really getting out of my comfort zone. I've never done this. I can do electromagnetic induction and I can work with the radar data and I don't know what, but AI, wow, it scares me. So I don't know how many of you feel the same as I do. But obviously not maybe the ERCs, right? But should we then have a summer schools for a non-student of how to do easy stuff with it so that we're not so afraid of using it? How do you feel about this? Or are we all just so different that there is a billion of applications that are all have nothing to do with each other, and I just have to force myself and put my hands into this and figure it out. Go to GitHub and do some coding.
That's a very good point. Thank you for raising that, and you're certainly not alone feeling like that. When I was a student, I remember my professors said that when you have students, you learn a lot, and that's obviously the case. But it's a very good point that development is going really fast, and just to get a basic understanding here and basic tools is also important. So that's a very good suggestion to have some hands-on workshops. Who will do that? I don't know, but it's a very good point that either the Arctic ROOS, EuroGOOS, or other organizations could probably organize something like that. So very good. Any others who want to chime in on that?
If I could say something just along those lines, sorry, I can't raise my hand because I can't find the button. I do think that there's some people who are very keen on using the AI tools, and then the people who are used to the traditional tools, and maybe the overlap is not so established just yet. I would be keen to hear from people, particularly with forecasting systems, who are reluctant to adopt it and why, or if everybody is on board and wanting to adopt these methods, and it's maybe more of a limitation of skills or time to develop skills and things. Because I suppose we've had some presentations today of people who are actively putting these things in forecasting platforms, which is great. And I think that there is, as the list of questions suggests, there are some things that can be done now, some things that will be done in the future, but there probably are some things that can't be done at the moment too. And it would be nice to hear a bit about that. Perhaps I should say, these questions, we've had a long afternoon, and these questions we will send to the speakers afterwards for inputs. So you don't need to give everything now. Yeah, I'll stop talking now.
Anyone else? And if you don't find your hand tool, you're free to speak out. But I think also relating to what Polona raised is one thing is the sort of technical skills to do it, but more importantly, I would say also understand it so that you use appropriate methods for certain types of problems, because doing something that won't work is not worthwhile. So having that kind of understanding as well is very important. If there are no other comments or replies to these kind of questions, and we do acknowledge that it's not necessarily easy to answer fundamental questions on the fly. As Heather said, you will be given the opportunity to provide inputs later on. If there are no further comments or questions, I don't think we should uphold you longer than needed. I don't know, Anna, if you want to say some wrap-up words.
Oh, yeah, I had those minutes, right. No, thank you for my side as well. Many ideas and thoughts raised within this afternoon. No, we want to just, I see Alicia has actually put the EuroGOOS workshop here, although it's limited to the EuroGOOS community. There is an artificial intelligence and machine learning webinar from the EuroGOOS side also on operational oceanography tomorrow. And what we are doing there together with the science advisory work group will be to see if we can merge our contexts into a white paper of some sort that they used to do after their webinar series. So we will keep in touch with you guys also about that in case you have the capacity and the will to contribute to such an overview paper if we move along those terms. So that is one of the steps forward we're going to take. And as said by Heather and Vidar, we will also repeat these questions and welcome input if you find the time and inspiration to put anything more than already done. Thank you for those thoughts, both in the chat and in the fora. So yeah, for sure, I think we're going to return to the AI aspects along the line here. It's extremely nice to ventilate all the developments, both sea ice and ocean and everything in between, right? So no, I think we are all positively overwhelmed by the afternoon. So that will be that from my side, at least.
I would like to thank to all the chairs and participants and speakers for being here today. It was really a pleasure to learn from all of you. And just as a reminder, we will share the video and the recording on our YouTube channel, and also the presentations that we have in the folder. So as soon as we have them, we will share it with you.
Perfect. No, thanks. I think we're closing down if nobody wants to stay. But have a good afternoon.
Thank you all.
Or evening.
Thank you.
Yeah, thank you very much.
You.
Thanks, everyone.
Goodbye.